Hello everyone, I'm Chris McIntosh. I help teach the statistics courses. This week we're going to go over your week 13 computer assignment. So our objectives for our week 13 assignment is to conduct a simple regression in Jamovi, interpret the results for a simple regression, report the results for a simple regression, and interpret a Bayes factor for a simple regression. So we're going to open up the data set, and this week I'm going to demonstrate on a data set that comes from page 178 of the HEVI text, but you are going to answer questions on the data set that's on page 181 of the HEVI text. So what I show on the screen is not going to match exactly. The steps are going to be the same, so you're going to want to follow along, but you're going to use the data set that I provided, and that just comes from page 181 of the HEVI text. So you want to download and open up that data set. And I have this open here in Jamovi, and you want to add your name to this. So let's go to Analysis Exploration and just get the results heading up there and click on the front of it and add your name. Okay. The statistical analysis checklist has the steps for simple regression on it. So you should have updated your copy of this by now. So questions for section 1 of the checklist: the study information, study purpose. We don't have a really purpose on this one. This is a learning exercise, so all these data are fabricated and results are not generalizable. But if this were for something real, then you'd have a purpose and you could speak to generalizability. Research questions for the demonstration. The research question would be, does cost go up over time? For your assignment, the research question that you'll be trying to answer is, does blood lead level, BLL, in the data set predict IQ? Study design for this demonstration. Nothing's really described in the text, but from the description in the chapter, this would be some kind of descriptive design. It's not experimental or quasi-experimental. And for your assignment, no study design elements were described in the chapter. Since it's dealing with lead levels, it would be unethical to randomly assign people to a group to receive elevated lead levels. So this would most likely be a descriptive study design. And ethical considerations, nothing was described. Data collection and handling, nothing was described. So answer questions in section 2 of the data set, the data set information. So variables and levels of measurement. So in the demonstration data set, we have 2 variables listed. One is month, and that just goes from 1 to 12. And I'm just going to call that continuous with an integer. And the other one is cost, and I assume that's probably measured in dollars. And I'm also going to call that continuous. And you'll just want to decide what they are for your assignment data set. Data accuracy, descriptive statistics. Since these are continuous variables, we're going to get descriptives on these so we can move month and cost over in the descriptives dialog box, and double check we're getting mean and median, standard deviation. Since we are going to do regression, normality will be one of our assumptions, and we can see that both of these, we have a non-significant Shapiro-Wilk test, so we do not violate our normality assumption. And it's always good to look at plots. The plots for continuous data are histogram and box plot. And I don't see any month is pretty flat with no outliers, and cost is also pretty flat with 2 outliers. So That's okay. And I might just I guess make this note. When I was looking at this, this was not my favorite example used in the Heavy text. One of our assumptions for correlation and regression, the observations are independent. I don't know. These are I'm still on the fence about this. These are over time and a cost. Maybe they're not necessarily related to each other. I just this time variable, sometimes you can have some relationships there, but I think that's probably okay. So, sometimes there's a lot of gray areas in statistics and you have to think about it a bit. So I think we're probably okay. If this were the same people over time, we'd be violating our independence of observations assumption, and we'd probably need to account for that in the model, but I think we're okay here. Okay. Missing data, we didn't see any missing data. Outliers, we didn't see any outliers. And since we're doing regression, it's good to see the correlations between your predictors and between your predictors and your outcome variable. So we got a correlation matrix by going to analyses, regression, and correlation matrix. And let's put our month and our cost variable in there, and you will use the variables in your data set and get this correlation matrix. We're getting a Pearson correlation. I'll have it flag the significant correlations, and let's get the correlation matrix plot. And I always like to get the densities and statistics on that too. And we can see that between cost and month, they're very highly correlated, 0.992. So we're going to expect to see something in our regression equation. We can tell already. And we have a linear relationship there. You can see there's no strange looking relationship. And we're also going to pass our homoscedasticity assumption, but we can look at that when we get to the assumptions. Okay, so good to look at the correlations. I don't see any issues that we'll be having when we get to the test. Okay. Answer the questions in section 3 of the test information. So test selection. So we already, you should have updated your checklist, but we can take a quick peek at that because that's always good to get comfortable understanding our which statistical test checklist or table. And in this case, we have one dependent variable, our outcome variable, and one independent variable, our predictor variable. And you see that I have added this test down here with our outcome is continuous, so that's going to be both interval and ratio. And I have added the simple regression test to all the levels of measurement, nominal, ordinal, interval, and ratio, because you can use any level of measurement with an interval level predictor. When it comes to the nominal and ordinal, you have to do some special coding, change codes into ones and zeros, and if there's multiple categories, you need to make extra, they call them dummy codes, to account for that. We're not going to go over that in this class, but be aware that you can use categorical variables in your regression equations. So this is a very flexible tool because you can use a continuous outcome variable with any level of measurement and run a regression and handle that. So also note that we've done this categorical variable with a continuous outcome variable with 2 groups. We did an independent t-test, and with 3 or more groups we did an ANOVA. You can actually do an ANOVA on a 2 group, in which case the results are pretty similar. And you can also do a t-test, use a simple regression on the same data. It looks quite a bit different, so you have to go kind of match it up, but once you do it a couple times, you see how it corresponds with each other. But just be aware that often you have more than one test that at your disposal. As a practical guideline, if I'm choosing which test, I would typically choose the simplest test that's appropriate for the data, and that's mostly for interpretability sake and being able to present those results to a wider audience. More people will understand it if you do it as a t-test than they will understand it as if you do it as an ANOVA or a simple regression. So just for interpretability sake and more and hitting a wider audience to make it more understandable, I'd go ahead and select the easiest test possible, just as a practical consideration. But let's go ahead and check StatCat and see what StatCat recommends to us. So we're going to click on StatCat and Jamovi and go to relationships, prediction, and group comparisons, because with regression we're doing prediction. And our outcome variable is cost, and our independent variable or predictor variable is month. And you'll see that we have two continuous variables here. We can do our Pearson correlation, which we saw last week, but we can also do a linear regression analysis. So that's great. Jamovi or StatCat and Jamovi steered us right. So our independent and dependent variables, they're both continuous. Test assumptions are the same as they were for correlations. Our sample is randomly selected from the population. You know that from the study design. Observations are independent, known from the study design. When you're answering this question for yourself, these are probably a convenient sample, and we know the observations are independent. So for your Canvas questions on your assignment, there's no issues there. Don't mark those as issues. Data are normally distributed. We're okay here. You'll need to answer that for your own test, your own data set. Variables have a linear relationship. We looked at that scatter plot, and Jamovi and StatCat gave us a little scatter plot. That's pretty linear, but we did look at our scatter plot before, and that also looked pretty good, so you'll need to look at that for your own data set. And homoscedasticity, we did not have any problems with these data points deviating far from the line on one end or the other, so we're okay, and you'll need to answer that for your own data set. So the null hypothesis significance test, this is where things are a little more complicated than they've been with the other tests that we've looked at. And I did. Okay. So I've made two slides for this because we actually do these steps basically twice. And this was something that I realized. It just kind of helped me group it in my head as a student myself. And when we're doing regression, we kind of go through this process twice. Once for looking at the model overall, and once for looking at the variables in the model, or the parameters or the predictors. They're using that same language, but we do it once looking at the model as a unit, and then we do it once looking at the individual parts of the model or the individual variables. And so we're gonna I've split this into two slides. This first one looking at the model, and then we'll go to the next one and look at the parts of the model. So the null hypothesis, and we're gonna, I guess this is a good place to explain to you guys, regression, we're going to change the language a little bit and move into this little more sophisticated language of model building. And we've actually been doing this all semester long. We've actually been building models all semester long, but we haven't used the language. It's a little more technical. And regression, you can see this. It's a little more explicit. And when I was a student, I wondered, why do they have so many words to describe the same thing? And we call them predictors, we call them independent variables, we call them dependent variables or outcome variables, and I just wondered, why do we use so many terms? And the reason is that the t-test and ANOVA models were used in experimental research for quite a while, And regression models were used in observational research quite a while, and they didn't realize that the math was equivalent for a while. And so these two areas, these two types of statistical analyses were used in different areas of research for a length of time before they realized that they're actually analogous to each other. And so you have this two different sets of language, and then mix in that different fields use these analyses, and they'll use slightly different language. So I actually do enjoy finding research from other fields and just kind of look at it. And sometimes if I run across a test name I don't understand, I look it up and I realize, oh, it's something I actually know about. We just call it something different in social and behavioral science, which nursing falls broadly into that category. And we really cross a lot of boundaries in nursing. So that's why we have so many terms. Part of the reason, at least, that I've been able to discover. So we're looking at this model overall. And the null hypothesis, there is no difference between the model with predictors and the null or the intercept only model. So we talked about this. I'll just go back to the slide so we can look at the equation for a line or for a regression. Oh, sorry, it's not in this one. It's in my other lecture. Just remember the equation for the line had the y equals mx plus b. We need an intercept and a slope, and the intercept only is when x equals 0, what's the value for y? And that's the same thing in regression. When the predictor variable is 0, what is the value for your outcome variable? And they make this, that's the null model, and the model with predictors includes the intercept, but it also has the variable with the slope. And so the alternative is there is a difference between the model with the predictors and the null model or the intercept only model. Our criteria for rejection is alpha 0.05. So you can tell we're doing a hypothesis test on this. And we're going to go to analysis, regression, linear regression, and turn on model fit so we can get that. So we'll go to analysis, regression. We'll go to linear regression, it's the third one down. And our dependent variable for my example is cost, and my independent variable is month, and you'll need to use the variables for your data set that are the correct predictor and correct covariate or predictor and outcome variables. And you want to go down to model fit. And we want to turn on this overall model test, this F test, and turn that on. So our criteria rejection is alpha 0.05. So if we look at the F test for this model, we have an F value of 594. That's a pretty high F value. Degrees of freedom are 1 and 10, and then our P is less than 0.001. So we're definitely going to reject the null and say there's a statistically significant difference between the null model, the intercept only model, and the model with predictors that is the model that we're testing right here. And then we're going to look at this R squared value. So remember with Pearson correlation, we used a little r. And now we have a big R. And right now, we're just looking at the relationship between one predictor variable and one outcome variable. So if we go back and look at our Pearson correlation, which we calculated here, it was 0.992. And not surprisingly, when we just have one predictor and one outcome, the big R for the relationship between the predictors and the model is the exact same as our correlation was between those two variables. When we start adding multiple predictors in, you're going to see that the individual correlations between the predictor and the outcome, the predictors and the outcome, have their own values, and this big R is not going to match any of them. So this is taking a combination of all those and seeing what is the overall relationship. But just as in regression, we can figure out what's our percent of shared variance, and so you'll take the R and you square it, and we get our big R squared, and that's also called the coefficient of determination, and it's kind of the multivariate version of a correlation. and 0.992 squared is going to be 0.983. So we share 98% of the variance. I mean that, and this is not real because you're never going to see it that high. If you see it that high, it's fabricated. So, and this is fabricated. So we have a very high coefficient of determination, a very high percentage of shared variance, which would be, we interpret that from R squared, and 98% or 98.3% would be our coefficient of determination. And R squared, big R squared, that's our effect size for a regression model overall, and that's our percent of shared variance. And we can go ahead and get the base factor for this model. We'll come back and look at the model coefficients in just a second. Well, you know what? I'm going to hold off on the base factor, and we'll just do that when we get done with the coefficients. Okay, so now we can do our NHST steps for our predictors, our model parameters. And the null hypothesis is, remember, B0 or B0 was for our intercept. And we're going to have one of these for each predictor in the model. So we have it for the intercept, and then we have it for each of our predictor variables. And so we're going to have one in this case, and you will have in your thing. So there's actually two sets here, one for the intercept and one for the slope, in case you just change that to B1. And our null is B0 or B0 is equal to 0, and our alternative is B0 or B0 is not equal to 0. Our criteria for rejection is alpha 0.05, and we're going to go, we are going to get analysis regression, linear regression, and we're going to look at the model coefficients, and we want to turn on one option there. So we're already in linear regression. You know, if you've clicked on something else, click back on the output in linear regression, and you're back in there. And we do have another thing for model coefficients, and we want to turn on the standardized estimate. I guess I should have done a better job and looked at the actual assumptions first. There we go. And we're going to turn on the normality test and the QQ plot. So we're going to talk about some of these others next week when we get into multiple regression. But so our assumption checks, we have our Shapiro-Wilk test. That is not significant. And our QQ plot looks okay. So you'll have to see how they look for your data set. But in this demonstration version, we pass. Okay, now that I looked at those assumptions, now we can finish up with our model coefficients. So the first part of that, we looked at our model fit measures, and now we're focusing on the second table, this model coefficients. And in different statistical software, they may give these things different names, but you're going to get a table that has information for the model overall, and you're going to get a table that has information for the variables in the model, or the predictors, or the covariates. There's all these different names, but you're always going to see these two main sections in different statistical software. So the trick is kind of learning what you're looking for, and then you can find it, even if it's in different statistical software and they call it a different name. I think I did mention to you in the lecture part that SPSS uses B for the unstandardized estimates, and it uses beta for the standardized estimates. And as we saw from the HEVI lecture, that can cause some confusion sometimes, and people can make some mistakes. And Jamovi bypasses that a little bit, and I looked in R, it also bypasses that somewhat, and it just calls it an estimate. And then Jamovi's very explicit in giving a standardized estimate. So R doesn't even automatically give you a standardized estimate. You have to go calculate it yourself and do something else. So this is a little easier than just using the R programming language. So our intercept, the null is that B is equal to 0. The alternative is B is not equal to 0. And we get a t-test on this. And we can see that we have a t-value of 16. And the p-value is less than 0.001. So statistically significant. The intercept definitely belongs in the prediction model. And then month, we have a t-value of 24, which is high, and not surprisingly, we have a low p-value, and so that is also statistically significant. So when you're reporting the results for a statistical parameters or covariates, you're going to have this t with the standard error in parentheses after it, the t-value, and then p equals in your p-value. And probably most often when you see the results for a regression model, because there's only one model here, you usually won't see that in a table in an actual research report. You'll see them just tell you that the model test was significant, and they'll give you the F value, degrees of freedom, and P value, and then they'll give you the big R squared. But often they'll report the model covariate information in a table just like this. So this is what you'll see most often. You won't see it really described in a separate narrative. So we would definitely reject the null on both of those and say they are statistically significant and they're both significant predictors in the model. Okay, now let's go and just see the Bayes factor, which is really easy to get in Jamovi. If we go to regression, Bayesian linear regression, and our dependent variable was cost and our independent variable is month, you'll use the ones for your model. And you'll see that I get one for BF and M. I think that's for the Bayes factor for the model. And it is, and you'll see we have the null model here, and then we have the alternative model, which is the one that includes the predictors. So we really just care about that one. 1.15 with exponent to 7 places, so that's a very big number. If it's a small fraction, it'd be like this, where it's scientific notation where it's negative, and this is a very small number. So this is definitely supporting the model with the predictors in it. And then this is the Bayes factor for our month predictor, and it's the same number because it's only one value in the model. So not surprising they're the same. And you'll see it gives us an R squared value, and it's the same as we had above. So a big Bayes factor supports the alternative hypothesis that the model is a significantly better than the null model. Okay. So the data that you're running your example on is the same data that they made a table. So if you go to page 188 of your Jamovi text, you're going to see that the second table on that page has a couple mistakes in it, actually. So they put the standardized coefficients label over the wrong column. It should have been one column to the right over the beta column. They put the value 0.913 under the constant row. It should have been one row down. The reason, and we can look at this right here on this output for our model predictors, you'll see when I got the standardized estimate, the intercept is blank. It doesn't have anything. And the reason that is when you're standardized things, think about a correlation that's standardized. When you have, or a z-score that's also standardized, you have a mean of 0 and a standard deviation of 1. And so if the intercept is been switched to be a mean of 0, then it's always going to be 0 in the standardized estimate. And then month, we get a standardized of 0.992, so that's almost one standard deviation away. I don't know if these are, I don't think these are standard deviations, but it's really big value. And so there's quite a difference between that. So in any event, I just wanted to point out that that table on page 188 of HEV, it has a couple errors, and they put that value of in the wrong place, and compare your results with that table, and you'll see that your results in Jamovi are more like mine than they are like HEV's. That's a mistake. And this is one reason why you can't just blindly trust what's in print. So this had to go through an author, editor, manuscript reviewers, typesetters, and publishers, and it made it all the way through and got to print to us with a pretty good mistake in it. So be prepared to double check things sometimes, because mistakes happen and it gets past multiple people. So it's not it's unfortunate, but it happens. So I just want to make you aware of it. Okay, so what's our so what? What is this telling us? So the model is significantly better than the null model. Our percent variance that we talked about was 98% of shared variance between the predictors and the outcome. And you'll need to figure out whatever value it is for your assignment data. Our intercept was statistically significant, so it's an important part of the predictor model. And each predictor in this example was statistically significant. What is the prediction equation? So the prediction equation is the outcome variable cost would be equal to the intercept 108.8 plus the covariate for month 21.7 times month. So predicted cost equals 108.8 plus 21.7 times whatever month it is. And you'll need to do that same prediction equation for your own data to come up with the prediction equation for your assignment questions. And what's the standardized estimate of the predictor? And in this case, month, the standardized estimate is 0.992. So we'll talk more about these standardized estimates next week. They don't mean a whole lot in simple regression. And I haven't tried this out, so we'll just try what we've been doing up to this point and reporting results. And let's see how ChatGPT does with interpreting some regression output for us. And I think I gave you some example, a sample report in the checklist. So that, that's an example there. But let me get the try the prompt I had on the slide here. Whoops. I think I hit enter instead of shift enter to go down to the next line. Okay, let's try giving it our model fit measures, and let's right click on the table, hit copy, and then click in there and Control V to paste, and shift enter to go down to the next line. And we'll right click on our model coefficients table and hit copy, and Control V to paste, and let's just try that, see how it goes. So it told us the model was statistically significant, F110, 594, P less than 0.001, that's correct. Indicating that month's significant predictor of cost. The regression equation was cost equals 108.8 plus 21.7 times month. Fantastic. That is the correct prediction equation. The model has excellent fit, indicating that 98.3% of the variance in cost was explained by month. A very large effect size. That is a very large effect size. The regression coefficient for month was significant. Again, I probably wouldn't okay, T was 24 point T. Okay, so one little difference here is this gave us degrees of freedom. I think it gave us degrees of freedom rather than the standard error. And typically what I've seen reported is T with the standard error and 24.4. So if I were reporting this, then I would report T with 0.891 in parentheses equals 24.4, P less than 0.001. So close ChatGPT, but not quite. So yeah, I gave you the correct format in the lecture slides and in here. Statistically significant strong positive relationship between month and cost. Each additional month was associated with an averaging cost of 21.7 units, which is basically interpreting it as a 1 point increase in month, or each additional month is associated with a 21.7 point increase in cost. The model explains nearly all the variance in cost, indicating that time month is a highly predictive factor for changes in cost over this period. And so that's not a bad write-up. This was not a fatal flaw. Just it's a little different than what what the standard is that I've seen. So with the exception of that one mistake, this isn't a bad write-up. I would, smooth it up a little, turn it into a narrative, a smooth paragraph, but I'm not dissatisfied with that. That would get you really far down the road in understanding what this regression was telling you. So copy your interpretation or reporting text and click in the bottom of your Jamovi output so you see the cursor blinking, and Control V to paste it. And then you're going to want to save the Jamovi data file, save as, and save that, and then save the PDF of your output, and that's under the hamburger menu export, and go save your output, and then go answer the computer assignment questions and submit your PDF output in Canvas. So that was, it's a little longer to do, but regression is a very flexible tool, and there's a lot of research questions you can answer with it. Sometimes they're focused on a model overall, in which case you'll see that model overall part focused on when they're talking about it. And sometimes they're focused on certain predictors and what they do, and so you see that predictor part. And so you'll kind of see both parts in there, but you really should get them both reported to you in a research article. So there's a lot you can do with regression equations, and that's why there's a lot to remember about it. But I hope this is helpful. It's been fun going over with you, and we're going to expand on this next week and do multiple regression with more than one predictor. And have a good week, and we'll talk to you guys later.